Good day all and welcome to my channel. Today we are going to be looking at the concluding part of our chemical equilibrium video. In our video 1, we looked at the introduction to chemical equilibrium, we looked at the Le Chatelier's principle, how the different constraints can affect a system already at equilibrium, and we looked at some other aspects too. But in this our concluding part of our chemical equilibrium video, we'll be looking at how we can derive equilibrium constants and how we can actually show the relationship among the three properties of a system at equilibrium, talking about equilibrium constant, free energy, and electrode potential. And then we also look at the calculations involving chemical equilibrium constants. All right. So you just stay tuned as I run through the series of these this concluding part of our video. On the board, let's start with looking at deriving equilibrium constant. Now, the derivation of equilibrium constant was credited to two scientists, namely Cato Maximilian Goldberg and Peter Wage. Now, these were the two scientists that the derivation of equilibrium constant was credited to. And then they came up with the idea of, checking those substances that can appear in equilibrium constants in a given reaction at equilibrium. And then they came up with actually a law known as the law of mass action. And what does this law state? Now, simply put, the law of mass action states that the rate of a chemical reaction is directly proportional to the active masses of the reactant. I go all over that again. The rate of a chemical reaction is directly proportional to the active masses of the reactant. So I can say that the rate of reaction is directly proportional to the active masses of the reactants. All right. Looking at this expression, we can simply say that the active masses of reactants can be likened to the concentration of the reactants raised raised to the power raised to the power of their number of moles. I will explain this better because it is very difficult for you to obtain the active mass of a reactant. The only thing you do is that you can take the equivalence, because the equivalence of active masses of reactant is given to be the concentration of the said reactant raised to the power of the number of moles of such reactant. That was their expression on the law of mass action. So, looking at that, I'm going to give you an equation, and with this equation, we better understand what these two men stated on their law of mass action. Looking at this, let's say you are given A plus B to give C plus D, and then let's say this is N, this is M, this is P, and this is Q. Now all these letters coming before the main letters in the reaction, they are the ones that are acting as the number of moles of the substances there. So I can say the number of mole of A is N, number of mole of B is M, number of mole of C is P, number of mole of D is Q. Let's just picture it this way, that all of them can appear in chemical equilibrium. And what does that mean? It means that the rate of the forward reaction must be directly proportional to the active masses of the reactants. Look at this. We are having double reactants and double products. Yes. Going by forward reaction, the reactants are A and B, and the products are C and D. Going by the backward reaction, the reactants are C and D, while the products are A and B. All right. So considering this very well, you get to know that if I want to obey the law of mass action, now the rate of the forward reaction would be directly proportional to the active masses of the reactant. By forward, this is forward, and this is backward. So going by forward, the reactants are A and B. So I can say A, concentration of A, and concentration of B raised to their respective number of moles. The number of mole of A in this case is N, so raised to the power of N, and the number of moles of B in this case is M, raised to the power of M. So in summary, I can put it this way, that arrow, which represents the rate of the forward reaction, arrow F, directly proportional to concentration of A raised to the power of N multiplied by concentration of B raised to the power of M. Please, when you are working with concentration, the bracket that you must use as a symbolic representation of concentration must be a square bracket, something like this. It's wrong for you to use a round bracket, or it's wrong for you to use curly bracket. Very, very wrong. It's even wrong for you to use something like this. All right, so these are unacceptable in representing concentration. So the only one that is acceptable is actually the square bracket. So this is for the forward. Then what about the backward reaction? You would agree with me that the rate of backward reaction would be directly proportional to the active masses of the reactants. You know, going backward, these are the reactants, while these ones are the products. So work with C and D. So that becomes concentration of C raised to the power of P dot concentration of D raised to the power of Q. All right. So that is, so if I want to use the symbolic representation, I can just in simple term like this. That's what I did here. All right. So we are having something like this. Good. So, you know, in mathematics, they don't work with proportionality signs. So we need to introduce a constant in this case. So drawing it from there, by the introduction of a constant, my rate of forward reaction will be equal to then K, which is equilibrium constant of the forward reaction, Kf, since we are working with forward, then A raised to the power of N dot B raised to the power of M, right? Then while for the other one, which is for the backward, of course, this is actually backwards, sorry about that. So that becomes arrow B is equal to, then we have KB, which is equilibrium constant of the backward reaction. Then we'll now work with our C P dot D Q, all right? So we have already gotten a standard reaction here. So we can actually call this equation 1 and call this equation 2, all right? So going by that, then we can simply come to this place now, and then remember that for equilibrium constants or for equilibrium reactions, the rate of the forward reaction must be equal to the rate of the backward reaction for you to say that the system is at equilibrium. So we already know that, okay, we have our value of the rate of forward is equal to the rate of backward. Remember, this thing is indicating that the system is at equilibrium. Rate of forward reaction must be equal to the rate of the backward. Already we know our value of the forward reaction in this case, in this equation 1 to be, so we can impute it here. It becomes Kf, then concentration of A raised to the power of N multiplied by concentration of B raised to the power of M, then equal to, our arrow B in this case is Kb, then concentration of C raised to the power of P, then multiplied by concentration of D raised to the power of Q. So from here, we can actually draw out something to get a common equilibrium constant of this reaction. Remember that equilibrium constant EKEQ is equal to equilibrium constant of the forward reaction over equilibrium constant of the backward reaction. So from here, we can get our generalized equilibrium constant of this reaction to be very easy, in that we can just take this one to the bottom in order to have this standard ratio. We bring this one to the bottom of this and bring the whole of this to the bottom of this. So interchanging that becomes Kf over this Kb. Now we now have this one, then equal to, we are left with this. So equilibrium constant, that is in terms of concentration of C raised to the power of P dot concentration of D raised to the power of Q, then over will bring down this one. Just like we are interchanging, then this one is coming down. You get? So that becomes A raised to the power of n dot b raised to the power of n. So remember that this stuff, we got it from here. That is our generalized equilibrium constant. So we can simply just replace the whole of this with this. So that becomes KEQ, which is equal to concentration of C raised to the power of P dot concentration of D raised to the power of Q over concentration of A raised to the power of N dot concentration of B raised to the power of N. So this is the derivation of the equilibrium constant of that reaction. But mind you, oftentimes students only know that when you are carrying out your equilibrium constant, you want to represent equilibrium constant. You always have the concentrations of the products at the numerator arm over the concentrations of the reactants at the denominator arm. You see the process of how we got it. So it means usually the products are usually at the numerator arm, then while the denominator constitutes the reactant. Again, very important, solids, solids and liquids do not appear in equilibrium constant. Do not appear in equilibrium constant. And why is that? Because their concentration is taken to be unity, which is 1. So it means that for solid species and for liquid species, they do not appear in chemical equilibrium. So the only ones that appear in chemical equilibrium are aqueous, and gases. All right. So these are the only species that appear in chemical equilibrium in terms of the constants. All right. So now that we've seen that, then I can actually give you a question on that so that you play with. Let's look at a case study on Haber process, talking about N2 gas plus H2 gas, then to give NH3 gas. Balancing directly, you have something like this. Let's say you are now asked the question, determine the equilibrium constant, of the reaction above, all right. You are given this kind of question and you are told to determine the equilibrium constant. It will be very easy because all of them will appear in equilibrium constant. Why? They are all in the gaseous phase of matter. So what are you supposed to do? The product over the reactant, remember, so equilibrium constant is given by product being our NH3. You write this one first, you put in your square bracket, and then raise to the power of what? 2, then over, then while this one, N2 in your square bracket, then there is nothing here, so it's assumed to be 1, so you don't need to write 1 there. Then dot, then H2 square bracket raised to the power of 3. So this is the answer. Yes. Why? Because all of them can appear in chemical equilibrium constant. Then what about you're given this? Ion reacting with steam. Remember that ion reacts with steam. It doesn't really react with cold water. If at all it reacts with cold water, it will be very slow. So reacting ion with steam would end up producing an oxidized form of ion, which is Fe2O3, then plus H2. Hydrogen gas will be released in the process. This is solid, this is steam gas, while this is solid. So let's balance the reaction. We're having 2 ion there, so here should be 2. So 2Fe, 2Fe. Then we're having 2 hydrogens here, 2 hydrogens balanced. Then oxygen here is 1, over here is 3, so we can make here 3. So 3 oxygen, 3 oxygen. Now we have altered hydrogen. Hydrogen now is 6, 3 times 2 is 6. Then y here should be 3. So everything is balanced. Then let's confirm. We are told to determine the equilibrium constant, of the reaction. All right. Now, if we are told to determine the equilibrium constant of this reaction, how do we go about it? It will be very easy. In that you're only interested in gas or aqueous. Remember I said gas and aqueous, they are the ones that appear in equilibrium constants, not solids or liquids. So the first two substances you are supposed to eliminate is this. Why? Because this is solid and also this solid. Remember we are going with the forward being at the top while the backward at the bottom. So let's go. That becomes Keq is equal to the forward now, which is hydrogen. So in your square bracket like this, and raise to the power of what? What's the number of moles of hydrogen? 3. Very easy. Then over, we are left with water in the form of steam, H2O, in your square bracket. Raise to the power of what? 3. So this is the answer to the question. It's that easy. But a situation whereby you are given this, okay, check this one out. CaCO3, then CaO plus CO2. Now this is solid, this is gas, and this is solid. And then you are asked to determine the equilibrium constant of this reaction. It will be very, very easy. Why? Because this is solid out of point, out of point. We are only left with gas, and gas now appeared in the forward. So it means in this case, it becomes Keq equal to square bracket, CO2, then just like that. Why? Because we don't have any number greater than 1 there. So this becomes our equilibrium constant because this is the only one that can appear in equilibrium constant in that reaction. So it's that easy. So that's how you can check for more questions on this, and then you tend to understand this better when you start getting your answers to questions. You'll be very happy with yourself. So that's that about the equilibrium constant. Now looking at the next on the board, we are having three properties of system at equilibrium, and they include we have the equilibrium constant. So the first is equilibrium constant, equilibrium constant, and then which is denoted with the letter K, and then we are having the next to be free energy, which is also known as Gibbs energy, is denoted with the letter G, and then we have the electrode potential. This is denoted with the letter E naught, right? So there is relationship amongst these three entities, of which I'm going to be showing you guys on how to know how to link these properties together. But mind you, our free energy, the relationship between our delta G with that of our equilibrium constant, we first look at the relationship between these two. Then we'll now look at the relationship between these two, and we'll look at the relationship between these two. So this first two is what we are looking at now, the relationship. It is given by R minus RT, the natural logarithm of K. This is the relationship between the free energy and the equilibrium constant, where this represents change in free energy, and arrow represents is a gas constant value of about 0.0821 atm dm cube per mole per Kelvin. Or if you are not given this value, then it's a constant value. You can be given this 8.314 then joules per mole per Kelvin. These are the values of R. Then while T is temperature usually in Kelvin. Then while Ln is natural logarithm. Then while the K is the equilibrium constant. All right, so you can use this relationship to link up your equilibrium constant and your free energy. Then the relationship between the free energy and the electrode potential is given by delta G is equal to negative NF then E naught. where this letter G still represents change in free energy, then N represents the number of moles of electrons present in the electrochemical cell, and then while this is Faraday's constant, then while the E naught represents the standard electrode potential. And there is something you should take cognizance of. The standard electrode potential, when it is positive of an electrochemical cell, it implies that the cell is actually a spontaneous cell, meaning that spontaneity of a reaction is taking place in the cell. All right. Then, of course, a negative value of your change in free energy indicates spontaneous reactions. All right. So you should just take cognizance of those facts. So this one is still a relationship between the free energy and the standard electrode potential. Then, what is now the relationship between equilibrium constant and standard electrode potential? It can be gotten from here. Since we know that this value is equated to this and this is equated to this, then we can equate both values together. So that becomes our minus NF E naught equal to minus RT, then natural logarithm of K. So for we to actually make the standard electrode potential to stand on its own, we have to divide by negative NF. So when we do that, it becomes something like this, because we are trying to show the relationship between standard electrode potential and the equilibrium constant. So negative will cancel negative, then we are left with E naught, which is standard electrode potential, equal to RT, then natural logarithm K over NF. So this is the formula that shows the relationship between the standard electrode potential and the equilibrium constant. We are having them here. So in summary, all these values would be of help to those that are going to major on physical chemistry. So it's not really of relevance that much in this case. All right, but you should just still know them. It's very, very important. Lastly, we are going to be looking at calculations involving equilibrium constant. On the board, we are having two questions, and these two questions, we are going to treat them one after the other. To start with, let's consider the first question. The reaction between gaseous sulfur oxide gas 3 atm and oxygen gas 5 atm is to yield for sulfur oxide gas 2.5 atm is represented by this. So let's write the reaction SO2 plus O2, then to give SO3. Then balancing the reaction, you have this, and everything is balanced. All of them, they are in gases or gaseous phase of matter. And then looking at this, I guess some students will be surprised at the way I actually represented this reversibility using this sign. That is this sign. Now you can use this sign to represent reversibility. Yes, you can also use this sign to represent reversibility. You can as well use this to also represent reversibility, but you cannot use this to represent reversibility because this stands for resonance. So it cannot be used as a sign to represent reversibility, but these three can be used to represent reversibility. So take cognizance of that. All right. So it's obvious that each of them will appear in equilibrium constant. Now let's get it. KEQ of this reaction will be equal to SO3 square bracket raised to the power of 2 over SO2 square bracket raised to the power of 2, which is this, then dot O2 raised to the power of nothing. Why? Because you know this is assumed to be 1. So this is the equilibrium constant representation. So let's impute their respective values. We are giving sulfur oxide to be 3, oxygen to be 5, and sulfur oxide to be 2.5. So our sulfur oxide here would be 2.5. So 2.5 atm all in square over, then while this one is sulfur oxide being 3, so 3 atm all in square, then then oxygen is 5. So 5, there is nothing here, so you don't square it. The reason why we are squaring it is because of these two that appeared here. All right. So let's go. This becomes with the help of our calculator, 2.5 square, 2.5 times 2.5, that's 6.25. So this will be 6.25 ATM square. Why? Because opening the bracket with the ATM and opening it with this, it gives you that. Then over, now we are having, this is also 5 ATM as well. So we should represent the ATM there. So in this case, this becomes 3. 3 square is 9. 9 ATM square, then dot 5 ATM. So 9 times 5 is 45. So that will be 45 ATM cube. So that becomes 6.25 ATM square over 45 ATM cube. Why? Because ATM square times ATM, that's ATM cube. So when you cancel out the ATM square from here, you are going to be left with 1 ATM. Then 6.25 divided by 45, 6.25 divided by 45, that becomes 0.14. So we can go with 0.14 ATM per ATM. Why? Because of the ATM that is at the bottom there, so it becomes per ATM. All right. So that is that about that. That's for the first question. Then looking at the second question, let's quickly consider the second question. Considering the second question, given the equilibrium constant of irreversible dissociation equation represented by the equation given below, which is this, our hint was given to be 1.35 times 10 to the power of minus 5. So let's bring out the equation once again. AgCl, then solid, then to give Ag plus, then aqueous, then plus Cl minus aqueous. So in this case, the only ones that can appear in equilibrium constants are these ones, and of course forward over backward. So backward would not appear, so this is already out. So we are left with Ag, then plus dot Cl minus. So that's it. Why? Because they are both aqueous. So we are given the concentrations, each of them to be 1.35 times 10 to the power of minus 5, then times 1.35 times 10 to the power of minus 5. So all you just do is just to multiply 1.35 by 1.35. So that gives us 1.82 1.8225 times 10 raised to the power of minus 10, because 10 raised to the power of minus 5 times 10 raised to the power of minus 5, that's 10. Then of course this is minus 5 plus minus 5, that still remains 10. Following the law of indices, minus 5 plus times minus is minus 5, so that becomes 10 raised to the power of minus 10. So that's it about that. So this becomes the answer to the question. So we have just looked at two questions. You can try your hands on other questions as well, and then you see that there is nothing to actually bother yourself about calculations involving chemical equilibrium. So it's my hope that you've been able to understand this very well. You can revisit the video, rewatch, watch and rewatch for you to get the clear concepts thoroughly. All right. So it's my hope that you've been able to understand it better. Don't forget to like the video, share the video, place your comments in any area where you are not clear with. Place your comment, I'll be there to reply you. And don't forget to subscribe. If you have not subscribed, please do so and hit the subscribe button. All right. So I wish you guys all the best. Thanks for watching and stay tuned.